Adnan, I know you have it for a fact.
No.
Can you open it, please, the question? I wrote it down.
No, it's in the different, but this is the macro. Until it's possible to say.
You don't mind sitting there with the cable on you? Don't you want to move? No, yeah, or move it in the center. That's fine. Yeah. Guys, do you have that bullet question?
Yes.
Adnan, where? No, you took a picture.
It did.
I think I have.
So just go past those 100 selfies you took since the class, and you'll find the picture then.
I don't think so.
Alright, okay, if you say so.
No, I didn't ask. I wrote it on the book.
Okay, so bullet question is how much warmer would a 10 gram lead bullet traveling at 100 meters per second be when it strikes the ball?
Great. So what happens here is, here's the wall, here's the bullet, it's 10 grams and it's going how fast? 100?
Yeah, 100 meters per second.
No. This bullet here has what energy here?
Before it's moving.
No, as it's moving. And here,
Potential.
no potential.
It's at rest zero.
But it must have some energy because heat energy, so it's heat here. So in other words, the kinetic energy became heat energy. A half mv squared equals mc delta theta. And what's interesting is I didn't actually have to tell you the mass of the bullet because I can cancel it. So I have v squared over 2c is equal to the delta theta. The v squared is 100 squared, and what was the heat capacity of the lead?
128.
It was quite small, wasn't it? 128. So if the answer is delta theta,
8 or 9.
it doesn't matter too much. 129. Close enough, agreed. 10,000 over 258. So 4, that's roughly 4, makes it, it's about 40 degrees hotter. Now, can you just hit that in on the calculator since mine's not open yet? Yeah.
38.75.
So it's an extra, or if you prefer Kelvin, it's a lot hotter when it hits the wall, right? Like, what temperature would the bullet be at before you put in the gun? Well, it'll be at room temperature. So what's room temperature? About 20. In Ireland, it'll be about 20. So after it hits the wall, what's the temperature of the bullet now? It's nearly 60. Hence why in movies and so on that you sometimes get steam and heat coming out of the person's chest when they get a shotgun to it. It's because the bullet gets very hot when it impacts, because all the kinetic energy has to go somewhere. Now, it's not right to say all of the kinetic energy became heat, because some of it became something else. I wonder if you might... Sound, true, yeah. What else? Yeah, so what type of energy is that? When it's breaking bonds, it's kind of like a potential energy. Kind of. Anyways.
As it's moving, is it moving energy?
It's using a little bit of energy because of the air.
So what is it?
It's heating up the air slightly as it moves through the air. So it does lose a little bit, true. Yeah.
But how did it gain? How did it gain?
How did it get its energy to begin with? It was
No,
ca-
like the extra energy, the 40, 30, from where did it?
from hitting the wall, the kinetic became...
So from, not from the thing, like going through there.
No, not from going through the air. No. This would be at 20 Celsius all the way through the air until it hits the wall. Then at impact it becomes 60. Yeah? Okay. Will we look at the tutorial then for that one, yes? Do you have the questions open, please? Did you write this down, Adnan? Okay, Mir, you have this?
Yes.
Sorry, I'm so tired. I looked at you when I meant to look at you. Mir, you have this?
Yes.
And Iyad, I'm sure if you have this? Okay. So we'll have a look at the worksheet questions. So, the first one, part A. Do you have it, Mir? Mir?
Yes, just give me a second.
Okay.
Now, a mass of 50 grams, and mass of water 300 grams.
Whoa, so then there, we need to draw some pictures. Whiskey, 50 grams. Water, how much?
300 grams.
Uh-huh.
Espresso 100 grams.
Ooh, espresso, yes. 100 grams.
Yeah.
And then part A is how long would it take to heat the water from 10 Celsius to 100 Celsius by using...
From where to where? 10 to 100, yeah.
By using a 2 kilowatt kettle.
Okay. So, power is work over time. So, yeah, it is, yeah. Time is work over power. Work is MC delta theta, and the power is something we know. So, I'll write it underneath here. Is it the water? Yes. And that's 4181. And what's the delta theta? 90, yeah. And the power is 2000. So if we just hit all of that in on the calculator, let's see what we get.
56.
You sure? Seems pretty quick.
Yeah.
I mean, it could be.
Yeah.
Yeah, it is that? Okay. 56 seconds. So, about a minute. Well, I suppose it's only 300 grams of water. That does boil pretty quick. 1 minute, about 56 seconds. Okay. Part B. When you're ready. Is this like your lunch now? No lunch earlier?
Just fine.
Just what?
Fine.
It's big enough. Okay. You have this? Yeah. Okay, what's B then?
Apple.
The espresso. Yeah.
Ignore me, please. Yeah, go on, what's B? Do you have it there?
I think it's for the espresso.
It's asking how long would it take to heat the espresso from 10 Celsius to 80 Celsius by using a 3 kilowatt coffee maker.
10 Celsius to 30.
No, 80.
To 80.
70.
Okay, so it's the same deal. The time would equal the work over the power, which is MC delta theta over P. What's the mass?
0.1.
0.1. And then, and then, now do I tell you what the heat capacity of the espresso is, or do I say just treat it like water? Because it's coffee.
No, it's not saying anything.
I think it should be
Water.
plus stress.
Well, yeah, what's the question? I haven't got it. Can you read it to me, please?
How long would it take to heat the espresso from 10 Celsius
Okay.
to 80 Celsius
Water plus
by using a 3
Coffee
kilowatt coffee maker?
coffee is not like that.
Yeah, coffee's like water.
Yeah.
So I said I couldn't find what coffee is, so it's like water. So that's 4181, and it's from 10 to 80?
Yes.
So that's a 70 here. about 9.8 seconds. I mean, when you think about when you order a coffee from Starbucks, they don't really have to wait that long until the coffee starts pouring out into the little cups. You know, when they put it into the machine. You know what I mean? There's actually a name for that. I can't think what it is. It's Italian, but they put the coffee in and they put it into the machine.
That pressure, that has also pressure also.
Yeah. You know what? Next time you can count how many seconds it takes. You'll see. I'm estimating that at about 9.8 seconds. Okay. Right. What's part C then?
The cold whiskey at temperature of 20 Celsius is added to the hot espresso.
Okay, let me just... The cold whiskey at 20 Celsius and how...
Added to the hot espresso.
0.050 is added to the hot espresso, which is now at 80 Celsius. And how much espresso did we have? 100, wasn't it? 100 grams.
Yeah.
And the question is, what's the temperature?
What's the final temperature?
Yeah. So you mix these two together.
But it should be 70.
What?
Final.
What are you saying?
Because in the part B it's like 10 to 18 for the espresso.
Yeah, I just want the temperature right now. The espresso's now at 80. Yes? Yeah. Now, we mix these together and the final temperature will be X. Who is gaining and who is losing? Who will gain energy here?
The whiskey maybe.
The whiskey.
And then who's losing energy? The espresso. So the energy gained by the whiskey must equal the energy lost by the espresso. So you have what the heck was this? Oh, this is alcohol. The whiskey is practically alcohol. 2300 MC. Now, what's the change in temperature? X minus 20, because it will become X. And that should equal M, C, and this one is losing energy, so yeah, 80 minus X. So now we just have a linear equation to solve. So we have 0.050 times 2300 X minus 0.050 times 20 equals 0.100 times 481 times 80 minus 0.100 times 481 times X.
Where did the 2012 go?
That's the heat capacity of whiskey.
Yeah, I know, but it should be multiplied by 20.
Oh, thank you. I've missed 2300 in here. Right, we'll need to do some cleaning up here. Let me just do the ones on the right since I can see those first. Right, so that first one is 33448. And then this one here, well, that's obvious. It's minus 418.1x. And then here, what the heck have I done? Okay, 0.050 times 2300. So that one is, what did I just have there? 115, isn't it? Yeah, 115x minus 2300 times 0.050 times 20. That's 2300. So now if I bring this together, I'll have 115x plus 418.1x equals 33448 plus 2300. So then I get x will equal, I can take the x out here. So I get x equals 33448 plus 2300 all over 115 plus 418.1. fraction 33448 plus 2300 over 115 plus 418.1. 67 degrees is the temperature of the final mixture. Did you get this? Excellent. That was a bit hard, but unfortunately that is the type of question you would get in the exam on this topic. It's only hard because you have a lot of numbers. Continue? Yes? Okay. What's the next one? Part D, is it?
The whiskey coffee mixture now has the hot water added to it. What is the final temperature of this mixture?
So now we have whiskey, what else? Coffee, and then we add in
into hot mixture.
whiskey,
hot water added to it.
coffee, and then hot water. Now we know what these temperatures are, we just worked them out. 67, 67, and this one here. The hot water was at 100. So we mixed them all together. So who's gaining and who is losing? So the coffee, gain. The whiskey, gain. And the hot water, losing, yeah. So, I'm sorry, what was the mass for the coffee? It was 100 grams, wasn't it?
Yes.
So C. Now the final temperature at the end will be X. So it will be X minus 67 plus the whiskey is 50, and what's alcohol? 2300. X minus 67. That should equal what the hot water loses.
When I say like add the masses and I add the C.
No.
No.
No, it doesn't work, sorry. Well, you mean add this and this and add this and this? They don't add like that, I'm sorry.
They'll come common.
You could take out the X minus 67 if you like, because it's common. And then what are you left with here? The water is, how much water? 300, wasn't it? C, and then the theta is
Plus.
hang on, let me think. 100 minus X. So you were saying, Mir, that the X minus 67 is in common, so if you want to take that out you can. And you have 0.1 times 4181 plus 0.05 times 2300. That's equal to 0.3 times 4181 times 100 minus X. So you might as well just bring that underneath. So let's just see what we get there over here. Fraction I got 425. So I have X minus 67 times 0.425 equals 100 minus X. So I have 0.425X minus 67 times 0.425 equals 100 minus X. So I have 1.425X equals 100 plus 67 times 0.425. Celsius.
Can you remove the calculator?
Okie dokie, guys. I still think there's more to the question, right? I think I still have to drop the coffee out the window. Isn't that the next part? Next part? Right, what's the next part? Is this the last part? No, it's not even the last. It's not even its final form. Right, E.
The Irish coffee is placed on the window of the kitchen, which is 100 meters above the ground in an apartment. The Irish coffee is knocked out the window. How much hotter will it be when it strikes the ground?
100 meters?
Yes, it's 100 meters.
Yeah. Right, so your coffee is made of 3 parts. The coffee, the whiskey, and the water. Yeah, the coffee is the espresso. Now, all of these 3 things are at the same temperature. What did I say? 90.15, wasn't it? What was it previously? 90.2. Yeah, it was 15. 90.2. And they all have different heat capacities. That's 4181. That's 2300. That's 4181.
The coffee,
Yeah. Now, when it hits the ground, they'll all gain some energy. Yes? How much energy would they gain? Well, they'll gain potential energy. Yes? Do you understand?
yes.
So, the heat that they gain will equal to potential energy, because they're going to have some more heat down here, and they get it from the potential energy.
What do you want?
I want to know how much hotter will the drink be.
That is.
Yeah. So, we'll do it for the coffee first. M, 0.100. C, delta theta, that's equal to M, G, H. So could we get the delta theta here? Yeah. What is it? Can you hit it in for me? Well, you notice how the masses cancel actually.
Yeah.
So the delta theta will be roughly what you get? 2, 3, 4. Yeah, what you had to type in was 100 times 9.81, that's 981, over 4181, which you said was, sorry, what was it, 0.234 Celsius hotter. Now, when you do the same thing for the whiskey and the water, the only thing that's different in this final answer is what? That was for the coffee.
Well,
Just the... Yeah, because the M's cancelled. So what's not... so this one and this one will actually be the same. And what's the whiskey going to be?
981 divided by 2300. 981 divided by 2300.
0.426, and that's the change in the temperature of the whiskey. Now, which answer do you take? Well, none of these answers is the right one, because because the coffee and the water got a little bit warmer, and the whiskey got a little bit warmer, and then they're mixed together, and the final change will be somewhere in between the two. Not average. So let's have a look here.
Why between the two? Why not both?
No, because you can't have a drink that has one part warmer than the other. So,
yeah, but if they all gain this, like each part gain specific heat, then it's all in the same cup.
I know. So you can't have you can't say the coffee part of the cup is 2.2 degrees warmer and the water part is 0.4 because it's all mixed together.
Yeah, so we should add it.
And say 0.6? No. Why not? What,
When you drink.
I know.
Yeah, that's it.
Okay, why not?
let me put it this way. If you have a cold glass of water at 10 Celsius and another cold glass of Coca-Cola at 10 Celsius and you mix them together, do you make a warm glass of Cokie water at 20 Celsius?
No, it's
No. It says at 10. Okay. What about a 10 and an 11?
10.5.
Yeah, so you know then that these don't add together. It has to be somewhere in between. By your logic.
I thought that they gain each.
They do. But they get mixed together and there has to be some answer in between. Yeah.
The 0.4 give 0.2.
Yeah, the water will not be as much as this and the coffee will be more than this. Do you understand? Yeah. So, this question is, I made this one a tiny bit too hard, I feel. So what I'm going to do is I'm just going to estimate the answer. And again, I know you don't want to be estimating answers in the exam, of course not. But it is a very important skill in physics to be able to estimate something, because sometimes a problem is too difficult to do. You estimate and your answer is nearly perfect. There's a small error, but you have an answer, whereas previously you couldn't have had an answer. So let's use our best physics estimation here and decide what's a good estimation to make. So what we could do is, like you suggested, maybe we could take some number in the middle. But the question is, where in the middle? Should it be exactly in the middle?
Add them and divide it by 3.
It depends which one maybe is bigger. So let's look. This one is coffee and water, whereas this one is just the whiskey. So coffee and water together, how much is that? The water was 300 and the coffee was 100, so that's 400. Now what about the whiskey? How much was that? 50. But the heat capacity of the whiskey is quite small and the heat capacity of the coffee and the water is quite large. That means it's easy for the whiskey to change its temperature and harder for the coffee and the water. So the coffee and the water will gain temperature because the whiskey is warmer. You see the whiskey is higher? The whiskey is higher. So the whiskey loses energy and gives it to the coffee and the water. Now we've done these problems before, so I don't want to do another one. So this is why I'm suggesting just estimate the answer. But even though it gives the energy, it doesn't give enough to raise the temperature because you have a lot more coffee and water than you do whiskey. And the whiskey has a low heat capacity, meaning it doesn't actually have much heat energy in it. So if I was to estimate an answer, I wouldn't pick the middle here. I would say it's only 0.280. Yeah, like if you think about it, I'm only going to round this up to the, I don't even know if I'll go as far as 0.3. I think I would say the temperature change is roughly 0.3. It was, sorry, you said it and I got it in my head and I said I'm not going to do that. 0.25 is what I meant to say of a Celsius. Now you could calculate it. Do you remember the way we did it earlier where you say one gains equals the other losses? But I don't want to do the same thing again because this question is already so long. So I just thought this would be a good chance to practice some estimation. I don't know what I did last year. I have a feeling I estimated as well. But if we were to calculate it using the program, we can see it exactly. So to save our brain power since we're tired, let's type the equation in and let's see how close we are to the true answer. And maybe we'll shock ourselves. Who knows? That would be nice. Did you work it out? You feel like it's 0.3?
I feel like 2.875.
coffee for me.
Coffee, I'm thinking coffee, yeah. Whoever's closer makes the other person a coffee.
But you have to buy it, not
Okay,
make it
you know
for
what?
me in the picture.
You know what? Coffee. Alright. Coffee on me for whoever wins.
No. This is between me and Sharif.
Well, I'm not
Not
participating.
in
Come on,
the-
that's not fair.
Yeah.
Not from the future machine. In the Starbucks.
Starbucks!
Yeah.
I'm a poor physics teacher.
So you have to be a very good estimate.
You're right, I should put my money where my mouth is and see. Okay, let's calculate it then. So, we'll see. Okay, so first we have to say who's gaining and who's losing. So we'll do who's gaining. The coffee and the whiskey gain. Yes? So the the coffee's mask first. 0.3 times 4181, and it becomes X. Yes? Minus. It's gaining. Yeah. So X minus the previous temperature. Now 0.2 it's not actually 0.2, it's 90.2 plus 0.2. So let me just explain. Does that make sense to you? Yeah, because here it was at 90, the coffee. Imagine the coffee and the whiskey, is separate. What temperature is this at the beginning? 90. This one here, 90. When they hit the ground, this one is 90.2 and the other one is 90.5 or whatever. But they're mixed together, so it's not going to be 90.2 and 90.5 like we were saying. It's somewhere in the middle. So the temperature is 90.2 plus 0.234. That's right? I hope so. That's the coffee. Next is that's the water. Next is the coffee. Everything's the same except the mass has changed to 100. And that should equal what was lost by the whiskey. 50 times 2300.
0.0.
Thank you. Times 2300. And the temperature this time will be 90.2 plus 0.426.
How do we know that it's 90.2?
That was the previous answer. Okay.
What's your answer?
I'm seeing now, I'm giving it as a number, not
You
such.
asked me.
Alright, to be clear, I said 0.25 as I wrote on the screen, and you said 0.3.
Yeah.
So, if it's 0.275, it's a draw. More than 0.275, you're closer. Less than 0.275, I'm closer.
Alright.
90. We did something wrong here in typing the equation. No, 90.44 is the final temperature, so we have to subtract from it.
Yeah.
90.
So you win.
Okay.
Minus 90.15.
90.15.
What?
Because that was the temperature at the beginning.
Without rounding up.
Yes.
You win. 0.296. Very good. Cappuccino, is it?
Yeah.
Cappuccino, okay. I'm getting the smallest size though.
Okay.
Yes. Okay. Very good, Mr. Reed. So 0.296. Yes, 0.3 was a good estimate for it. Okay, is there more to this one?
No.
Was that the last part?
No,
There is one more part.
One more part? Okay.
But there is no much estimation. So,
Can we write it down?
Oh, yes, sorry, yeah. Don't worry, next year I'll get it next time. I'll remember now.
How we gonna...
I'll cheat the next student. What? There's one part left. Yep.
You make it bigger size and get bigger size later.
Yes, I can vente cappuccino. Oh, the last part is, I think, when it's left on the grass overnight, isn't it? Did you write this down? We'll do the next part and then we'll take a Starbucks break and then do the next lesson. Because I don't know about you, but we definitely need a coffee now. You're the same? It's been a long week.
Take 2.5 hours.
Oh yeah.
2.9.
No, roughly 2.5.
Okay, roughly 0.3. Yeah. Okay, fair enough. Right. Did you see the upload from Fuang on my YouTube channel? No, Fuang wanted to do the tutorial. So if you look at a video, so it says featuring little PH. This is Fuang teaching the tutorial. She wanted to do it, and I said, okay, be good practice for your English. You go ahead and do it.
Oh, she solved the homework.
She solved the homework for the class.
And you check it?
You can listen to her English.
Mm-hmm.
I was sitting down, making sure everything was okay.
I asked her, no, everything is okay. I said, oh, it's easier for you. No,
What is the name of that?
Featuring little PH.
That's the one. Let's hear it. What's the last part there? F, is it?
Must watch.
Must do it. Must read this.
Might want to skip forward 1 minute because that's when she says she wants to do it. Yeah, that one. Oh, is it not sound?
No, that was like somebody was writing.
Oh, that's a lecture. Oh, that's not the lecture. That's something different. That's efficiency video. You must have clicked the wrong one. That one here. I found it too talking. Well, you're finding it there. Let me do the last part. What's the last part there, Mir?
It is a rather cold night. The ground is at a temperature of 1 centigrade.
1 Celsius?
Yeah. The coffee will give heat energy to the ground until thermal equilibrium is reached. How much energy has the coffee gave up to the ground?
So the question is, how much energy does it lose? So the coffee, the whiskey, and the water all lose energy, and they all decrease from 90.5 to 1. So you have delta Q equals MC delta theta for each of them. So first, coffee. What's the mass of the coffee? 0.1. 4181, and it's 89.5 plus, what one's next? The whiskey.
Why is 89?
Because it goes from 90.5 to 1. Next is the whiskey. And finally is the water. So how much energy is lost when everything goes down to 1 Celsius? So we'll just hit this in the calculator and see what we get.
So everything will just go down to 1 too?
Yeah, because the ground is at 1 Celsius.
Won't like the area will take down to
Yeah, so that's why I said it's left overnight. So
Ah.
everything reaches equilibrium.
And then it's not MC delta Q equal MC delta Q for the one, or it's just
No, I just want to know how much energy is lost. So it's just loss. There's no gain here. Adnan said the ground is the gain. We're not considering that. Yeah, but the energy lost by the cup equals the energy gained by the ground. That's why I said overnight, so that energy kind of just disappears into the earth. I'm just looking at the loss. What is it? 4181, 89.5. Actually, 89.5 is in common to everything, so I can just take that out. Plus 0.05 times 2300 plus 0.300 times 4181 times 89.5, and that's a lot. It's 160 kilojoules. Now the reason is water, remember I said, can hold a lot of energy, and this water was very hot. It was going from 90 to 1. So you don't really appreciate it, but hot water has lots of energy in it. Lots of energy. This Irish coffee that I made in the story has 160,000 joules of heat energy in it. That's a lot, that's a big number. This is why it's so expensive to heat water. It's the biggest cost on your energy bill. Making tea, making coffee, having a shower. It's or heating the home. Heat is the biggest cost, at least in a place like Ireland anyways. Okay, so we'll take a Starbucks break, and then yeah, but you have to pay for air conditioning, which is I think just the same, just as energy